Welcome. In this video, we're going to take a look at Chapter 5, problem number 20. At 46 degrees Celsius, a sample of ammonia gas exerts a pressure of 5.3 atm. What is the pressure when the volume of the gas is reduced to 1/10, 0.10 of the original value at the same temperature? Alright, so for this problem, we're going to divide it up. We have two stages. We have our initial stage, which we'll call stage 1. And then we have this second phase, so we'll call that stage 2, all right? And at these different stages, like stage 1, the initial stage, has like a certain pressure, has a certain volume, has a certain temperature. And some of those values change when we go to stage 2. So to organize ourselves, let's make this chart. So let's see, what is our pressure at stage 1? So pressure at 1. We look up at the problem and it says, a sample of ammonia gas exerts a pressure of 5.3 atm. So perfect. We got 5.83 so got our first value in the chart. And notice it says atm. atm, atmospheres, that's the perfect unit. Whenever we deal with this ideal gas stuff, we always want to have our pressure in atm, our volume in liters, and our temperature in degrees Kelvin. All right, and then in moles and moles. So we have atm, perfect. Alright, now what's our volume? And this is where it gets trickier. Because we look at this and let's look at the problem. They don't really tell us anything about the volume. They tell us the volume of the gas is reduced to 1/10 of the original value. So we have a problem here. What do we do? Well, when we don't have a number for something, let's just put in a variable like math class. So V1, and I'll say V1 equals V1. Perfect. Alright? Very creative. Let's keep going. What is temperature at 1? Alright, and if we go up to the problem, it says 46 degrees Celsius. So perfect, 46 degrees Celsius. Alright, but we look at this, and one thing, the key word here is degrees Celsius. Whenever we're working with this, put it in Kelvin. End of story. So we do 46 plus 273, and that leads us with 319 degrees Kelvin. Okay? So chart side for 1 is none. Alright? Now let's go into chart 2. So what's our pressure at 2? Alright? We look at the problem and let's see. Oh, the question is what is the pressure? So pressure is an unknown, so we'll put a question mark. Now it tells us that volume at point 2 or stage 2 is 1/10 of the original value. So this is kind of the key of the problem. Volume is 1/10, meaning it's V1 over 10. So if it's 1/10, it's 1/10 times V1, or we can write this as 0.10 V1. Okay? Now, what is T2? Let's see, at the same temperature. So we look at this and like, okay, T2 doesn't change. Now when we look at this problem, one thing that's kind of tricky is that we don't really need the temperature. Because we have the values for pressure and volume, we're just missing one pressure, and temperature stays the same, we can use Boyle's law. The temperature is just there to just kind of throw you off. So let's ignore our temperature. So can I just ignore it? Okay. Let's talk about Boyle's law. Boyle's law says, so Boyle's law basically says that for an ideal gas, P times V, pressure times volume, stays the same when temperature is constant. Okay? So we have a situation where temperature is constant. So we can say that the pressure times volume, so P1 times V1, so these two, the product of these two equals P2 times V2, which is the product of these two. And so this is nice because we can now substitute our values in. So P1 is 5.3. V1 is V1. P2 is a question mark, so we'll call it P2. Or you could call it like X or something. And then V2 equals V1 over 10, or 0.10 V1. All right, now what are we solving for? Let's look at the problem. It says, what is the pressure? So we're solving for P2 right here. So we divide to get P2 by itself. So we do divide by 0.10 V1, 0.10 V1, and so we have P2 equals, and I'll put everything in parentheses so it's easier to see, 5.3 times V1 times 0.10 times V1. Alright? Now, this problem is kind of weird because usually they give us a value, like a number value for volume. But they didn't. They forced us to use variables. The reason we can use variables here and get away with it is because these volumes will cancel. So if they give us a thing where they tell us about the proportion, like something, you have an original, then you have 1/10, then that's kind of a screamer or a hint that we should use volume 1 as a variable. So we have them cancel right here, volume 1 and volume 1, and we're left with 5.3 divided by 0.1, P2 equals 53. So is that our answer? No. 53, and what are your units? ATM. So let's look back at the problem. What is the pressure when the volume of the gas is reduced to 1/10 of the original value at the same temperature? Well, we looked at the problem. We first made a chart. We made a chart of our values at 1, our initial state, and values at 2. We then realized that temperature was constant, so we could use Boyle's law, which basically is like P times V is constant. So P1 times V1 times equals P2 times V2. So these guys are constant, so we can set them equal. We solved it out. Because of the way the math worked, the volumes canceled, and we're left with 53, and of course we need those units, 53 ATM. And that's your answer.